Alright, so what's poppin', guys? So today we'll be doing trapping rainwater, which is a hard question, and when I did it, it took me quite a while to understand it, so let's go through it. So the question is that, given n non-negative integers representing an elevation map, where the width of each bar is 1, we want to compute how much water it can trap after raining. So what exactly is an elevation map? An elevation map is, given an array, right, like this array, each number represents a height of a wall. So we can see that at index 0 is going to have a wall of height 0, so there's nothing here. Then 1 represents there's a wall of height 1, then it's going to be 0 again, then a wall of height 2 represented here. So we keep on going through the array, and basically what they're trying to ask is, let's say we have this structure of this elevation, after it rains, how much water can it trap? So these blue blocks are the water that is trapped. And each block of water is trapped between two main walls. So you can see that for this region of water, it's actually trapped between these two walls of height 2 and height 3. And the reason why it cannot go above here is because, let's say you have another block of water here, right? It's going to overflow over this block 2 and it's going to go off, and therefore it doesn't trap it. So the trick of this solution is really looking at each region of water and finding the limiting wall of either the left or right wall that's limiting it, such that it can only hold up to that height. So let's look at an example where it's easier to understand. So given this array of 4, 2, 0, 3, 2, 5, what it represents is that we have this region of height 4, 4, then height 2, height 0, height 3, height 2, and then a wall of height 5, like this, right? And we want to find the region of water that it traps. So in this case, the region of water is only this part. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 areas of water it traps. Therefore, the answer here is output of 9. So how do we calculate this water? The trick here is to really go through each column of the elevation map and find the maximum left wall and maximum right wall, and then find the minimum of those two enclosing walls. So we know that each block of water, each column of water has to be trapped within two tall walls. That's how it's being trapped, right? So for each column of water, we're going to find the left trapping wall and the right trapping wall. And based on these two enclosing walls, we'll find the minimum of the two. So because, let's say for this column of water, right? You see this column of water? The left trapping wall is going to be of height 4, and the right trapping wall is going to be height 5, right? And the reason why we chose height 4 is because this is a limiting wall, right? Because it is shorter, therefore anything that goes above height 4 is going to overflow. So we're going to keep an array of this, right? So we can see that there's a wall. It's going to be 4, 2, 0, 3, 2, 5. This is the height of each wall, each index that we're going to look at. And then we're going to try to find the maximum left wall for each column. So let's say for this column, the first column, what is the maximum left wall? It's going to be 0 because there's no walls to its left, right? Therefore, we're going to traverse through the array forward to backwards and keep track of a maximum left wall array, right? So we're going to keep track of array, variable called maximum, max L, and then we're going to initialize it to 0. So when we first encounter 4, we're going to just fill it up with max L, which is 0, because there's no walls to the left. And then we're going to move forward and we're going to check, is the current wall 4 bigger than the maximum L? Yes. Therefore, we want to update it to length of 4. So now the maximum left wall that we have seen is 4. Then we go on. We're going to fill it up first, and then we check. Is 2 greater than 4? No. Therefore, we don't have to update the max L. So we go on forward again. We're going to fill it up. Max L is 4. Then we check. Is 0 greater than 4? No. So we move on. We're going to fill in 4 again. Is 3 bigger than 4? Nope. So therefore, we want to update it and then go to the next one. 4. Is 2 bigger than 4? No, right? Therefore, we just update it. And then lastly 4. And then once we've reached the end of the array, we know that we have filled up the maximum L, maximum left wall. So what this array represents is that, look at this. For each column, the maximum left wall is going to be at this value. So for the first column, it's going to be 0. Then it's 4, 4, 4, all the way. Why? Because for each of the column, other than the first column, the maximum left wall is always going to be 4, right? Which is always referring to this wall. So no matter which column here, the max L is going to be 4. So this is what the first row, this array represents. Then we're going to do something very similar, but for the maximum right wall. And to find the maximum right walls, we have to start from the end and move forward into the array. So we're going to keep a variable called max R. We're going to initialize it to 0. And then we're going to go backwards, right? So at first, is going to be 0, right? Because for the first wall here, there isn't any wall to the right. Therefore, the maximum right wall height is 0. And then we're going to compare. Is 5 greater than 0? In this case, yes. Therefore, we want to update the max R to be 5, because we've seen a wall that's greater. Then we move on. We're going to fill in 5, right? Because look at this next column here. The maximum right wall is 5. And we check. Is 2 greater than 5? No. Therefore, we don't update it. We move forward. Then we 5. And then we go through the array very similar to the first time. And we can see that it's going to be 0, 5, 5, 5. So what this represents is that other than the first wall, other than the last wall, the maximum right wall for all the other columns is going to be 5, which is referring to this. So after finding these two, right, we want to find the limiting factor. Because for each column we already found the left and the right wall that's constraining it, right? We want to find the minimum of either the max left wall or the minimum of the max R, max right wall. So for each column, let's say this column, the minimum of the max L and max R is going to be 0, right? Because here, there is no left wall here, therefore it's going to be 0. And for the next column here, let's say we're looking at this column, the maximum left wall is 4 and the maximum right wall is 5, right? Which is a limiting wall? It's obviously going to be the one that's shorter, because whichever one is shorter, it cannot go over it, if not it will overflow, right? So we'll fill it up with 4, and we do the same for each of the walls, right? And so we end up with this. So what this represents is, you see this 4, 4, 4, 4, it actually represents the amount of water it could potentially hold for that column. So this column can potentially hold 4 units of water. But the reason why it cannot hold 4 is because there exists a wall here that's actually blocking the way. Therefore, if you look at this, right, you can see that there's technically an area of 4 blocks of water, 4 by 4. So this can actually hold 16 units of water, but then we just need to minus off the walls that are currently in that column. So what we have to do is, once we've found the potential height of water, we must minus off the current height, the current wall height. Okay, so then with this information, we can start doing the calculation. So the minimum is gonna be this array, this row, right? And then the current wall is just gonna be this value that we look here. So we just do the minus, 0 minus 4, this equals to minus 4. So the reason why it's minus 4 is because it technically means that there's 4 blocks of water, right? So if it's negative, we just want to ignore it. We want to round all negative values up to 0. Then we move on. 4 minus 2 equals to 2. So this 2 represents that you see there's 2 blocks of water here it can hold, right? So this 2 represents, after you take this 4 and you minus the wall here, we get left with 2 blocks of water that it holds. Then we move on to the next one. 4 minus 4 is 4 minus 0 here is just gonna be 4. So this column holds 4 units of water. Then we move on. 4 minus 3 is 1. 4 minus 2 is 2. 0 minus 5 is negative 5, which we round out to 0. So finally, if we add all the numbers here, 2 plus 4 plus 1 plus 2, this will give us 9. Yeah. So this 9 represents the 9 units of water that it holds here. Yeah. So this first solution works. And it runs in O of n solution. Why? Because we're just looping through it twice, right? 3 times actually. So the first loop is to find the maximum L, the second loop is to find the maximum R, and the third loop is to find the minimum, and then calculate the amount of water it actually holds. So it runs in O of 3n, which is just O of n lah. Right? It's a linear time solution. However, the space complexity is O of n, right? Because we're keeping 3 of these arrays, right? 3 of these arrays that we need to keep track the maximum L and maximum R. So there's actually another way that uses 2 pointers that runs in O of 1 space complexity. So it still runs in O of n time complexity, right? Because we have 2 pointers that loop through the whole of the array, but it will keep track of 2 pointers and it will update the max L and max R according to the 2 pointers, and therefore we don't have to hold any extra memory to keep track of the arrays and keep track of the max L and max R in arrays. We keep track it using a pointer value. So let's look at how the pointer solution will look. So we'll still look at the wall, but let's just delete the table. So we're not gonna look at the table anymore, because the table is the extra memory space, right? We're just gonna keep track of 2 pointers, left pointer and a right pointer, which is gonna initialize to the end and the start of the array. we'll still keep track of the maximum L and maximum R. So they're gonna be initialized to the value at the left pointer and right pointer. In this case, the start of the 2 pointers is 4 and 5, therefore it will just leave it at 4 and 5. Right? And then the reason why this 2-pointer solution will work is that we're using this formula. So let's look carefully at what this formula is actually saying, and then we can find the solution using the 2 pointers approach. So the first part of the solution says we want to find the minimum of max L and max R. So let's look at the current max L and max R. It says 4 and 5, right? The minimum value is going to be 4, right? So can the maximum R be bigger? Of course, right? Potentially here could be a 6, right? And then you know the max R eventually is going to be 6. But at this point, we know that the minimum is going to be 4 and 5. And that 5 cannot be smaller. This maximum right wall cannot go down because we're always keeping track of the maximum, right? So this is the maximum, it's the smallest value it can get. Therefore, when we compare 4 and 5, you know that 4 is always going to be the minimum in the first part of the solution. Therefore, we're going to go through it and then we're going to calculate it based on the current pointers. So LP and RP is going to start at the start and end of the array, and we can do the calculation directly. So let me erase the previous calculation that we did. And let's start. So looking at LP and RP, we want to find the minimum of max L and max R. So the minimum is going to be 4, and the current wall is going to be also 4. Therefore, 4 minus 4 is going to be 0. So it holds 0 amounts of water. So after doing that, we want to ask, should we move the left pointer forward or right pointer forward? We will move the pointer that we have checked. Because we already checked this wall, right? So we don't want to check it again, therefore we move the pointer forward. If we were to check RP, that means if RP was a smaller value, we will move RP forward. So but in this case, the maximum L is smaller than the maximum R. Therefore, we know that this is the limiting factor. Therefore, we check it, therefore move it forward. And next, we can check here. So we update the maximum L. Is 2 bigger than 4? It's not. Therefore, we do have to update the maximum L, and you can do the calculation. So the maximum L is 4, minus the current wall is 2. Therefore, the amount of water it holds is 2. And then we move the left pointer forward since we've checked it. So now, we update. Is 0 bigger than 4? No. Therefore, we do have to update the maximum L. Therefore, we can just do 4 minus 0, which is just 4. So this column can hold 4 units of water. And then we want to move the left pointer forward again. Is 3 bigger than 4? No. Therefore, we don't have to update the max L. And so we can just do 4 minus 3 equals to 1. So it holds 1 unit of water. Then we move left pointer forward once more. Then we see, is 2 bigger than 4? No. Therefore, we do have to update the maximum L. So we do the calculation, 4 minus 2 is 2. And then we move the left pointer forward. And once it has converged, right? So we check it one more time. This time, you see that 5 is bigger than 4. Therefore, the max L has to be updated to be 5. And then we do the check. What's 5 minus 5 is 0. Therefore, we have done the whole calculation. Left pointer has approached right pointer, and then we can stop the thing. We can sum it all up. 2 plus 4 plus 1 plus 2 equals to 9. And so that's the solution. And we can see that it only uses 2 pointers to keep track. And then as it traverses, it looks at the max L and max R. Then it uses the fact that it is a minimum to then do the calculation and just sum out the result. So let's look at how that code might work for the pointer solution. So for the pointer solution, we'll need 2 pointers, right? LP equals to 0, and the right pointer is going to start at the end of the array. So the length of height minus 1. Right? So that's the index of the end of the array. We want to keep track of a variable called result. So this is a sum of the water that we have checked. And we want to do while the left pointer is smaller than the right pointer. So while they haven't crossed each other, we check if max L is smaller than max R. So we also want to initialize 2 variables to keep track of the maximum left and maximum right wall we have seen, right? So we're going to initialize to the max height of the left pointer, and max R is going to initialize to the height at the wall at the right pointer. So if max L is bigger than max R, right, we want to do the comparison here at the max L part. But if the maximum right value is smaller than the maximum L value, we do the comparison on the right pointer. So first, if max L is smaller than max R, we want to increment the left pointer first by 1. And then we want to update the maximum L. So now we're doing the check here. Is 4 bigger than 4 or 4 bigger than 0, right? So we want to update max L to the maximum of max L and the actual current height, which is the height at left pointer, right? And then we want to add it to the result. So the formula says we want to find this minimum minus the current wall. And since we know the minimum is gonna be the max L, right? We can just do max L minus the current height. So it's the height at the left pointer. And basically, if max L is bigger than max R or equals to, that means we know that the right pointer, the max R, is smaller than max L. Therefore, we can do the reverse. So we're gonna do RP minus equals to 1. And then max R, update max R equals to the max of max R and the height at right pointer. Then we add it to the result, plus equals to max R minus the height at RP. And then at the end, we just return result. So this after we have added all. And for this case, we must actually check if not height. So they might give us an empty array. In that case, we just want to return 0. So that's a special thing that we have to do for this problem. So let's try running the code. And it should pass. If I submit it, you can see that it runs very fast at 81.52% and it uses a very less memory because it is a O of 1 time space complexity solution and O of n time complexity, which is the best we can do for this question. So I hope that helped you. It's a challenging question, but I think the ultimate factor to realize is that we can utilize this minimum function to use the 2 pointers approach, which really makes the question easier. So thank you.